Here's another example where we have as many outputs as we have inputs. So we have two representations of this. We can think about this as a transformation, not of the plane, but of three-dimensional space. So a transformation or a vector field. Which one we'll choose will depend on the context of what we're working with. So, but here's an example. Suppose we have our function. I'll give it a bold name since its output is bold. F of no, this would be a good one. How about f of rho, phi, and theta? And then we get our three outputs. Would be rho sine phi, cosine theta, rho sine phi, sine theta, and rho cos phi. These are actually the equations that you get for spherical coordinates, right? This is the x, the y, and the z. So, because remember, in spherical, the way that we represented points in x, y, z was if you had a point here, then you would measure the distance from the origin to the point. That's rho. You could look at the angle between the line from the origin to the point and the positive z-axis. That was our angle phi. And then we dropped down and looked at the shadow, draw this line, measure the angle that you make in the xy plane with the positive x-axis, and then you have your angle theta. So we figured out that by looking at this end on, here's your angle phi and there's rho, then the z value has to be rho sine phi, rho cosine phi, sorry, because it's the one that's adjacent to the angle, so rho cosine phi. If we drop down into the xy plane, then the rest of this acts as our radius in the xy plane. It's rho sine phi, and then the usual polar stuff applies, right? The radius is rho sine phi, so x is radius cosine theta, or r sine phi cosine theta, while y is r sine phi sine theta. So this is a transformation. Basically, we're starting with points in rho phi theta space and ending up with points in x, y, z space, the usual Cartesian space. Let's see. For example, a plane of constant rho, right, gets transformed. If rho is constant, that gets transformed to a sphere, doesn't it? So we have a sphere of radius rho over here in x, y, z. Since there's nothing that's locking down phi and theta, those are free. We just have a plane of constant rho. We have to walk out from the origin the same distance, but we can do that at any angle. So phi and theta are free there. So we get spheres, and we look at planes of constant rho. So if you take a different value for rho, constant rho, then you get just another sphere here. Okay, so planes of constant rho are turning into spheres. Planes of constant phi, if you lock down phi, then those are turning into cones. So those planes are becoming cones over here in x, y, z space. So if you change the value of phi, then the cone can tip out further. That's kind of interesting. And planes of constant theta then become planes through the origin. There's no lock on phi or on rho. They just become different planes through the origin. Whew, that's getting messy, but we can kind of see how different planes in rho phi theta space become different surfaces in x, y, z space. Cones and spheres obviously are things where spherical coordinates would be nice because they have nice representations in rho phi theta space for rather complicated objects in x, y, z space. Another way, when you have as many inputs and outputs, is to think of it as a vector field. Now this one is natural to think about as a transformation, but other functions might be more natural to think about as vector fields. Here's an example. We have, remember, in a vector field, the input is the location, and the output is a vector. So maybe given the location, we have x, y, and z. Oh, that's kind of dull, but we could look at some inputs and outputs and then visualize them in three-dimensional. I'm just making a table of inputs and outputs. So our inputs would be x, y, and z, and our output, think of those numbers as maybe u, v, and w, but they're pretty boring. They're just x, y, and z again. So let's see what it gives when we graph this. So we have, if we put in the point 1, 1, 1, then we get out the vector 1, 1, 1. If we put in the point 2, negative 2, 1, then we get out the vector 2, negative 2, 1. Putting in a vector maybe 1, 1, 0 gives out the vector 1, 1, 0, and so on. Let's just visualize this as a vector field. In a vector field, we think about the inputs as our location and the outputs are a vector, and so to depict it, we go to the location and draw the vector that we get there. So the location 1, 1, 1, we go to that location. Let's see, it's here. And then we have a vector that, in this case, the vector is 1, 1, 1. So we go over 1, out 1, and up 1. So we have a vector basically that just continues on in the direction that you would go from the origin to that point. Let's see, where was our other point? 2, negative 2, 1. So here's this location, and we have a vector. If you think about the vector that would carry you from the origin to your location, that would be the vector 2, negative 2, 1, and we've just taken that vector and put it on the end over here. If we were to see 1, 1, 0, 1, 1, 0, that's this location, and the vector 1, 1, 0 goes out. That's the vector that would carry you from the origin to that point, so the vector that we put there is the same as the vector from the origin to that location. You can see because of the special form of this particular vector field, we call this a radial vector field. It's always radiating outward wherever you are, right? You just get a vector that continues on in the direction that you came from the origin to get there. So we have this radial vector field to work with. So you could think like if you in three-dimensional space, if you start to fill it up with some fluid, right? Maybe that fluid is going to diverge from that single point and go out somewhat like that. Okay, so think of it as a fluid. Or also you could think about it, instead of thinking of it as a velocity of a fluid, you could think about it as some kind of force. So this might be a little bit like the force you get when you have a positive charge here, right? Then this would sort of indicate the force that other positive charges feel, right? It's just a way, positive charge at the origin, all these other positive charges want to get away from there as fast as they can, and so these arrows could represent the forces that they feel, although the lengths of these arrows isn't quite right. That's kind of the idea of this radial vector field. So as a transformation, you can think about, okay, the input and the output, and how do certain regions in the input space get turned into regions in the output space. Or if you have a vector field, you can just plot the inputs as a location and the outputs as a vector, which could represent maybe a velocity or a force that some object would feel or that would be present at that particular location. It'd be worth mentioning that this last vector field is actually a linear one. It has 3 outputs and it has 3 inputs, so you can represent it with a matrix that is 3 by 3. So you have a 3 by 3 matrix times your 3 by 1 vector or matrix of inputs, and you have a vector of outputs, u, v, and w, and in this case u is just 1x, no y, no z, v is no x, 1 y, and no z, and w is no x, no y, and 1 z. I think w came out funny there.